It's a great pleasure to give this lecture. I hope you can all see the slides fine and you can all hear me fine. And let me start by pointing out what I'm not going to talk about. What I'm not going to talk about is this paper here that just came out yesterday, I believe, in the Bulletin of Symbolic Logic. So if you're interested, go to their website and have a look. It's also a defense of logicism, and that's also the title of this paper, which I wrote with Uri Nodelman and at Salter in the US. But it's a different kind of paper. Okay, it's a different kind of logicism with a different kind of background logic, with different aims, and it's not a Carnapian logicism that we're developing in that paper, but you might still find it interesting. It also involves a nice technical part, an interesting, I think, model construction in the appendix. In contrast, my talk today will be very much on the philosophical side and much less on the technical side. So there won't be any new interesting technical results. Okay, it's not really a logic paper, but it will be something that firmly belongs into the philosophy of mathematics, in which I'm going to deal with a certain chapter that's given by Carnap's philosophy of mathematics. And that will be the topic of today. Okay, so that's the man. That's Rudolf Carnap. I mean, many of you will know him as one of the founders of the famous Vienna Circle, one of the founders of logical empiricism, more broadly conceived. And personally, I have some interest in Carnap. I've written together with Andrei Karos the Stanford Encyclopedia entry on Carnap. But I should say that I'm not really a historian of philosophy. And my interest in Carnap is not really a historical one. It's just that when I, once started reading him a long time ago, I became interested in some of his philosophical ideas. And I think they are still relevant if, suitably updated, as it were, and further developed. Of course, that's what we do in philosophy. We want to make progress. But, as a historian of philosophy, you might also find Carnap very much interesting. And in this field called Hoppos history and philosophy of science, he became a central figure in recent decades. And there's currently, I hope that's right to say, a kind of revival also of Carnapian ideas in systematic philosophy, like in formal epistemology or in metaphysics and the like. And my paper today will hopefully be a contribution to a kind of revival of some of Carnap's ideas in the philosophy of mathematics. But it will be a systematic talk, not a historical one. Now, this photo that you see here, that's the title page of the Schilp volume for Carnap. So these Schilp volumes, I think they sort of still exist today, but back in the day, certainly, they were very prominent in summarizing some famous philosophers' opus, philosophical work. And they typically started with a kind of autobiography of the philosopher in question. And then there were articles about his or her philosophical work. And then the philosopher would be able to reply to these comments. So that was the Schilp volume. And the photo that you see here is the title page of the Schilp volume for Carnap. And in his personal autobiography in the Schilp volume, what he says when he thinks back of the influence by Frege, of whom Carnap was a student, he says the following: I had learned from Frege that all mathematical concepts can be defined on the basis of the concepts of logic, and that the theorems of mathematics can be deduced from the principles of logic. Thus, the truths of mathematics are analytic in the general sense of truth based on logic alone. Or in other words, what Carnap is saying here is he had learned that logicism is the case. Because logicism is that kind of reduction, as it were, of mathematics to logic. And he says, I got it from Frege. And since he says that in 1963, which is already sort of the final stage of Carnap's career, it would more or less mean that he remained to be a logicist from the beginning pretty much till the end of his philosophical career, because he got to know Frege as a student. And then the late Carnapian is looking back and says, I had learned from Frege that logicism was the case, so which sounds very much like, and by the way, I, Carnap, am still a logicist. And I think that is what he wants to say here, okay? Logicism, he himself, Carnap, once defined as the conjunction of the following two theses. The first thesis, and that is one that was mentioned also in the quote by Carnap, mathematical terms are definable by logical terms. So that's a kind of conceptual thesis, right? You could also say the mathematical concepts can be reduced to logical concepts. And secondly, the other conjunct is mathematical theorems are derivable, logically derivable, that is, from logical axioms and definitions. Okay, and that's the second part. And that's not so much to do with concepts, but rather with theorems, right? The body of mathematical knowledge that we have. That's how Carnap describes logicism in his paper titled The Logicist Foundations of Mathematics, which appeared in Erkenntnis in 1931. Erkenntnis was the journal of the logical empiricists. And this paper derived from a talk that Carnap had been given at a conference in 1930, a famous conference where some other well-known philosophers of mathematics and logicians gave talks about the foundations of mathematics and the philosophy of mathematics. Heiting presented intuitionism, for example. Von Neumann presented formalism, and Carnap's job at the conference was to present logicism, so basically reflecting on Frege and Whitehead and Russell, and Ramsay and other people who worked on logicism and philosophy of mathematics at the time. The paper emerged from the talk, and both in his talk and in the paper, he would summarize logicism as the conjunction of these two theses. And that's still pretty much what people right now would understand by logicism about mathematics. It's the conjunction of the two theses, well, subject to some variations, right? So some authors say neo-logicists or neo-Fregianists like Bob Hale or Crispin Wright and others, they might, slightly revise maybe the first conjunct by saying mathematical terms are definable by logical terms and abstraction terms, because these neo-logicists, they very much try to reduce mathematics to logic and abstraction principles. And within these abstraction principles, you have abstraction terms, right? Or what they express is abstraction concepts, like the number of in Hume's thesis, for example, and the like, okay? And some logicists might want to revise the second conjunct by not so much focusing on mathematical theorems, that is what's provable currently in mathematics, but rather focusing on mathematical truths, okay? And then they would say, these logicists, mathematical truths are logical truths or maybe analytic truths or something like that. So they would put the emphasis on truths rather than theorems, okay? But, roughly something in that ballpark is still what we understand by logicism about mathematics to this day. And this thesis of logicism, as I've presented it on this slide, will be the background of my talk, okay? If you want to know more in general, historically, about Carnap's logicism about mathematics, there is this paper by Bonert from 1975, which is a nice summary of Carnap on logicism, and I can recommend it very much, okay? Now, what I want you to look at now is this part here that I've put in red now, derivable from logical axioms and definitions. Some people in the literature, and this includes Carnap at the time when he wrote this paper on logicist foundations of mathematics, they would summarize derivability from logical axioms and definitions sometimes by saying mathematical theorems are analytic, okay? And that's Frege's notion of analyticity that he presented, for example, in the Foundations of Arithmetic and elsewhere. So for Frege, a sentence was analytic just in case it was logically derivable from logical axioms and definitions, okay? And, in the quote that I had by Carnap on my first slide, that's how he presented logicism, right? Mathematical theorems are analytic. It's clear that for every logicist whatsoever about mathematics, definitions, that is, explicit definitions, will play a crucial role, okay? There is no logicism without explicit definitions, okay? So Frege didn't really reduce, strictly speaking, mathematics to logic, but he tried to reduce mathematics to logic plus definitions, Okay. Similarly for Whitehead and Russell, and as I said, for all other logicists. Okay. For them, definitions are as crucial as they are for mathematical practice itself, because as you all know, right, mathematics doesn't just consist of axioms and theorems and proofs and the like, but of course, a heavy load of mathematics is just given by definitions. Okay, and that's the same for logicism, and that's why we need to go beyond pure logic, as it were, if you're interested in logicism, because at the very least we need to add to logic explicit definitions. Okay, that is also why analyticity will play a major role in my talk. Okay, now sort of the historian background, as it were, is I'm sure well known to you, but just let me remind you of it. So the logical empiricists like Carnap, they all had Kant as a background, right? They were German philosophers. And as you know, for Kant, sort of mathematics like geometry and the like was synthetic a priori. Okay, so it was justifiable without sense experience. It's the a priori part. And it was synthetic. So the truths of mathematics, the interesting truths of mathematics, like Euclid's axioms or so, they were not true just in virtue of the meaning of the terms that were involved. They were not analytic, but they were rather synthetic. And of course, for Kant, analyticity actually had a slightly more restricted definition, right? Because Kant was only looking at statements sort of in subject-predicate form, and then would define such statements as analytic if sort of the predicate is included in terms of content in the subject. Now, this restriction to sentences in subject-predicate form, that was given up later, and for very good reasons. And one of the people who pushed that was, of course, Frege. So he had to define analyticity differently from Kant, and he did, and that's exactly what I just mentioned before, right? Analyticity for arbitrary sentences of very different logically complex forms was really given by whether or not a sentence is logically derivable from the logical axioms and definitions that Frege had put forward. Okay, and Frege was arguing not just not for logicism about mathematics overall, but he wanted to show that arithmetic was analytic. Okay, but Frege still thought, like Kant, that, for example, Euclidean geometry was synthetic a priori. Okay, so Frege wasn't a logicist about mathematics overall, but about a significant part of mathematics, namely arithmetic. Okay, and then there's further things that happen, Whitehead and Russell, and so on and so forth. So I'm fast forwarding now to the logical empiricists. So now we're in the 1920s, 1930s, and so on. That's where Carnap entered the philosophical scene. And what they wanted to argue for, much like Whitehead and Russell, was that all of mathematics was analytic. In fact, for the logical empiricists, there were no synthetic a priori truths at all. Okay, so this class, as it were, of this corner of logical space was not occupied by anything. Okay, so Euclidean geometry was not synthetic a priori, but it was geometry was analytic if it's done properly. Okay, and of course, Euclidean geometry as a mathematical discipline for the logical empiricists was not actually describing physical space, okay, but an abstract Euclidean space, a space of mathematics. Okay, and in general, for them, geometry became this part of modern pure mathematics as we understand geometry now, and it was to be distinguished from geometry of physical space, which was a part of physics, of course, and physics, of course, consisted of lots of synthetic a posteriori statements, right? You had to justify a relativity theory, of course, on empirical grounds, right, by observation and the like. Okay. Similarly, arithmetic for the logical empiricists was analytic. Okay, of course, analytic a priori, and in fact, all of mathematics was analytic. Okay, so this was the change, and this means the logical empiricists really defended different versions, though, but still versions of logicism. Okay, to the logical empiricists, to put it very simply and by glossing over details, were logicists. Okay. Of course, the devil is in the detail. Carnap's philosophy of mathematics is way more subtle. I will hint at that very soon. But you can see that logicism was an important part of the logical empiricist project. That's my point here. Okay, my aim in my talk is to argue for the following thesis. There is a logicist conceptual framework. I'll tell you later what I mean by that. in which all standard mathematical terms are explicitly defined from logical terms. Okay, so this corresponds to the first conjunct of Carnap's thesis before. And all standard mathematical theorems are likely to be analytic. Okay, so this corresponds to the other conjunct in Carnap's thesis before. But the notion of analyticity will not be Frege's notion of analyticity, but a different one. I call it sometimes Carnap analyticity, or you might call it semantic analyticity. Okay, because it's not spelled out in proof theoretic terms, it's not spelled out in terms of logical derivability, but it's spelled out in semantic terms. Okay, and that's the notion that Carnap introduced and used in his philosophical work once he had taken his semantic turn in the after he had got to know Tarski's work on truth and more generally semantics later. Okay, so roughly speaking, Carnap from the 1940s would be one of the most influential semanticists of his time, right? One of the originators of philosophical and also, in fact, linguistic semantics. And he was following Tarski there. And at that stage of his career, he would no longer define analyticity like Frege did, but in a more semantic fashion. And my notion of analyticity that I'm going to use to defend the second part of my thesis here will be a semantic notion of analyticity as well. Okay. What you can also see is that there is this component here is new, right? It didn't show up in Carnap's second conjunct from before, namely this probabilistic component, where I say all standard mathematical theorems are likely to be analytic. Okay, so at the end of the talk, there will be a probabilistic component to my logicism, and I'll tell you later why that is and why I think there are some good reasons for stating logicism in this slightly different way. Okay, now, how do I get there, right? I was just saying all standard mathematical terms, I want to argue, are explicitly definable from logical terms, and all the standard theorems of pure mathematics are likely to be semantically analytic in this logicist conceptual framework that I will be constructing. But how can I show that, right? And what are the standard mathematical terms and the standard mathematical theorems anyway? Okay. Now, what I have in mind here is something like, what you would get when you were to study mathematics and you would take the first few courses of mathematics, right? So, analysis, okay, and discrete mathematics and, linear algebra, okay, and then geometry in our modern sense, as I explained before, and then, probability theory, and then you move on, okay? There might be a point where you're leaving sort of standard mathematics. For example, say you become a professional set theorist, right? Then you might just as well say, well, I'm still interested in standard mathematics, but in my work, I go beyond it. Because, for example, maybe in my set theoretic work, I'm studying and to some extent presupposing set theoretic axioms that we do not think are generally accepted by the mathematical community. That's where you would go beyond standard mathematics in my sense, okay? One way of making this notion of standard mathematics, standard mathematical terms, and standard mathematical theorems more precise is the following one, right? What I really will argue for is the following. There is a logicist conceptual framework in which all mathematical terms from second order set theory will be explicitly defined from logical terms. And all theorems of second order set theory are likely to be Carnap analytic, that is semantically analytic in the framework. Okay, that is really what I want to argue for in the rest of my talk. Okay, and general wisdom has it that all standard mathematical terms, all standard terms that we have in pure mathematics as they are used right now by pure mathematicians, are definable in second order set theory. And standard wisdom has it that all standard mathematical theorems that we have in pure mathematics right now in 2025, okay, are actually logically derivable, okay, in second order set theory. Okay. And since this is so, I can actually argue for this thesis, and then by what I just said, get that all standard mathematical terms will be sort of reducible by definition logical terms, and all standard mathematical theorems are likely to be kind of analytic because, for example, the standard mathematical theorems will be derivable from second order set theory. And for the theorems of second order set theory, I will have argued in my talk that they are semantically analytic in the framework that I'm building. Okay, so this is the dialectic. Okay, so that is why I'm going to focus very much on second order set theory in my talk and sort of try to reduce it to logic plus definitions, as it were. That's the plan. Now, I should say this is a convenient way to proceed for me in my talk, because I get sort of all standard mathematics in one fell swoop, right, by one move, okay? But other than that, personally, I don't feel necessarily wedded to using set theory as a foundation of mathematics, okay? I'm a Carnapian also insofar as I'm a pluralist with respect to the foundations of mathematics, okay? So as far as I'm concerned, there's nothing like the right foundations of mathematics, but there are different clear and precise and systematic and fruitful foundations of mathematics available at this point, okay? And they might be pragmatically more useful or less useful for different purposes, okay? And there are purposes for which I believe the set theoretic foundations of mathematics might not be the most useful ones, okay? But maybe category theory is a better foundation of mathematics for these purposes, right? Or for other purposes, say homotopy type theory is a better foundation of mathematics, right? So, you know, for example, if you're into that, right, homotopy type theorists think that if you use homotopy type theory as a foundation of mathematics, then it will be easier to formalize proofs so that an automated theorem prover will be able to check a mathematical proof, which is an attractive feature, right? Whereas proofs of mathematical theorems, standard mathematical theorems in set theory, for them it might be way harder to actually check them by an automated theorem prover, right? So that might be a purpose for which the set theoretic foundations might not be the ideal ones or the best ones, right? And who knows, you know, in 20 years, some of you might come up with new foundations of mathematics that are even more useful than the ones that I've just mentioned, right? And so on and so forth. So the reason I'm using set theory here is just because it's a convenient choice. But don't read more into it, okay? So there shouldn't be a question later or maybe a criticism where saying, well, but your logicism only works for set theory and I have independent reasons for thinking that set theory is not a good foundation or so. Then you would criticize something that I didn't argue for, okay? So for me, this is just one convenient choice amongst others. In fact, as you're going to see, there will be something like a more general logicist strategy behind my talk. And this more general strategy would be applicable also to analysis of sort of mathematical language and mathematical theories, okay? Corresponding to other foundations of mathematics, but there might also be some applications of my logicist strategy of a more piecemeal fashion, right? So for example, maybe you want to apply my strategy just to the terms of second order arithmetic and to the theorems of second order Dedekind-Peano arithmetic, right? Then you use my strategy to argue for a new version of logicism about arithmetic, right? Or you could take as an object language of your interest the language of second order analysis, the second order theory of the real numbers. And the theory might be second order Dedekind analysis, okay? And then you use my strategy to argue for a particular version of logicism about, you know, second order real analysis, and so on and so forth, okay? So I think there is a more general message to my talk that will be hopefully, you know, interesting to you, even if you're not into set theory for whatever reasons, okay? But for me, it's a salient example to work with, and that's why I've chosen it, okay? But you might have noticed that in all of the examples that I've given, I mentioned second order, okay? So second order set theory, second order arithmetic, second order analysis. So there is something in my talk that will really rely on using second order resources, okay? And that will be a part of my talk. So if you don't like that at all, and you think you have very good philosophical reasons for rejecting that, then my program and my strategy might not be for you, okay? But I also hope to convince you along the way that you shouldn't worry about these second order resources. And I think it's fair to say that, you know, differently from the 1970s and maybe 1980s, right? Where people, in, you know, philosophical logicians at least, and philosophers of mathematics were very much tied to first order languages and first order logic. This has changed, okay? So contemporary logicians in philosophy, at least, and contemporary philosophers of mathematics very often make use of second order or, in fact, higher order languages, as, you know, logicians and philosophers of mathematics did back then at the days when Carnap developed his logicism, right? So think of, you know, Whitehead and Russell, right? Think of Ramsay, they were all using higher order logic in one version or another of type theory, and that is also what Carnap presupposed. I will return to that later. Okay, and these days philosophers are very happy using these resources again. So I don't think people these days are very much worried about, for example, using second order logic as a background language or so. Okay, and that's why I also feel free to use it. Okay, now let me stress that I will argue for my thesis here on sort of quasi-Carnapian grounds. That is, I will use some philosophical resources that were available to Carnap himself, but I want to emphasize, I want to stress that Carnap himself did not argue for logicism in that way, and the logicist thesis that I'm presenting on this slide is not to be found in Carnap's work. Okay, so this is not really Carnap's logicism that I'm defending here. I call it Carnapian logicism, or here I use an asterisk here to say it's quasi-Carnapian logicism, okay, to make the difference. So it's a logicism that Carnap could have defended, I think, because he had the philosophical resources to do so, but it's not a logicism that he actually defended in his work, okay? In fact, there is a nice paper by Benjamin Marshall where he gives some historical reasons to believe that Carnap would not have wanted to proceed like I will in my talk today. Okay, so as you're going to see, for example, I will think of membership, set theoretic membership, and set theoretic sethood. Okay, I will think of these two concepts as being given by a theory, namely the axiomatic theory of second order set theory. Okay, so I will think of membership and sethood as theoretical terms, the meaning of which is given by a theory. Whereas it seems, and that you can find in Benjamin Marshall's paper, Carnap did not think of the membership concept in that way. He thought you don't need an axiomatic theory to pin down, to determine its meaning, as it were. But rather, he thought already our pre-theoretic understanding of membership and of sethood was good enough to deliver sort of a uniquely specified concept, okay? And that's why you would not even want to try to determine, say, membership through an axiomatic theory, okay? Whereas this will be part of my project, okay? So, Carnap had the resources to argue for logicism in the way that I will, and also for the thesis that I want to defend, but he did not actually do so himself. The other final bit that I want to stress is, in his logical syntax of language, right, one of the major works by Carnap from the 1930s, logicism is something that he mentions as an option, but he also mentions other possible rational reconstructions of mathematics, not so much on logicist ground, but maybe, say, on Hilbert's formalist grounds, right? Or, as we would now call it, maybe realist grounds, okay? So roughly speaking, if you're Carnap, you can also be a philosopher of mathematics of a different brand, not so much of a logicist brand, but maybe of a formalist brand or of a realist, almost Platonist brand, and so on, okay? Of course, certain moves would then have to be made in order to satisfy Carnap's requirements of rational reconstruction. But in principle, he acknowledges that there is the option. Okay, so for example, Carnap discusses in the logical syntax of language the option, and actually that's the option that he uses and works out a lot in the book, of not treating, say, mathematical terms as something definable from logical terms, but rather as taking them to be primitive terms of their own kind without trying to reduce them to logical terms, right? So that's an option. Okay, in Carnap's terminology, he would then use a different language. Okay. In my terminology of my talk, you will then use a different conceptual framework. But for Carnap, as he puts forward in logical syntax, there's lots of languages available, right? There's a plurality in my terminology of conceptual frameworks, right? All of which can be worked out sufficiently clearly and formally precisely and systematically and so on. And they might be useful for, again, different purposes, okay? And there is no fact of the matter which of them is the right one to reconstruct mathematics within them, right? Which corresponds to the point that I made before, that for me personally, there is not the right foundations of mathematics, okay? And for Carnap, that's the same point. But I think it's also perfectly clear throughout Carnap's career, as I mentioned before, that sort of the logicist rational reconstruction of mathematics is an option. And actually, it's a good and interesting and useful and fruitful option for various purposes. Okay, and that's why Carnap thought highly of logicism. Okay, And so, we're still on Carnapian grounds when we're dealing with logicism in the way that I will in my talk, okay? And finally, don't forget, my talk is not a historical one, but a systematic one, okay? It's a systematic thesis that I have on my slide here, and it's this systematic thesis that I want to argue for. Okay, now here's the plan. In the first part of my talk, I want to deal with the first part of my thesis. I want to show you that, we can define membership and sethood in purely logical terms, okay? And I will first sort of, in the first part of my talk, introduce the idea of how this is done. And then in the second part, I will introduce a logicist framework in which this idea sort of gets implemented formally, okay? But first, I will deal with the idea of how we can reduce, as it were, conceptually, membership and sethood to logical concepts at all. In the second part, I will introduce the logicist framework, as I said, and I will also make clear what I mean by semantic analyticity and how this relates to Carnap's views on analyticity once he had taken the semantic term that I mentioned before. And then in the third part, I will argue for the likely analyticity of what here in this slide I call the Ramsey sentence. It's a certain kind of second-order existence claim, okay? And once we will have done that, we will have argued that this second-order existence claim is analytic. The analyticity of the second-order axiomatic system of set theory will follow from that, okay? And then I will have argued for my thesis. Well, the little proviso is, as I have it here in the title of the third part of my talk, well, I don't quite get, a derivation of the analyticity of this Ramsey sentence and then a derivation of the analyticity of second-order arithmetic, but rather I get an argument that I think shows that it's likely, right, that this second-order existence claim is analytic and that it's likely that, therefore, second-order set theory is analytic in this logicist framework that we've constructed, okay? And then in section 4, I will just briefly summarize the argument, and at the end, I'll draw some conclusions on what we have shown and what we have not shown, okay? I will only discuss pure mathematics in my talk, okay? So there is no applied mathematics. There is nothing about the application of mathematics in the empirical sciences or in engineering, okay? As interesting as that may be, this is, of course, also for a logicist an interesting part of the philosophy of mathematics. It's just that for reasons of time and space, I will not deal with that here, okay? And when I deal with set theory, accordingly, it's about pure set theory. So there will be no sets of Ur-elements or atoms where these Ur-elements or atoms might be other things than sets, okay? But I will rather deal with, right? Think of the cumulative hierarchy that starts with the empty set and then you build sets from there, okay? Those are the sets that I will be interested in, okay? There's some related literature. There are some versions of logicism out there that bear some sort of resemblance to what I'm developing in my talk. Especially there's work by Jack Woods, and also there's this paper by Bocconi and Woods. So if you're interested in how my paper relates to theirs, you might ask me about it in the Q&A later, okay? But other than that, I will try to develop my own logicism here and also show how it relates to Carnap's philosophy more generally, okay? All right, so that's the plan. Now let's get going. Let me start with saying a bit more about this axiomatic theory that will play a salient role, as I said, in my approach, and that is second-order Zermelo-Frankel set theory. Okay, so by that I mean this axiomatic theory. It's finitely axiomatizable, so you can think of it as a longish conjunction. Okay. Sometimes, by second-order set theory, people might mean, the set of all theorems derivable from these axioms in a deductive system of second-order logic. Okay, that's also fine with me. Some people might talk of second-order set theory, and what they mean is they take these axioms here, and then they collect together all sentences in the corresponding language that would be logically implied by the axioms in the model theoretic sense. Okay, in the model theoretic sense of the model theory of second-order logic. And that's not what I have in mind here. Okay, so I will not presuppose set theoretic model theoretic second-order consequence in my talk. That won't play any role. Okay, I mentioned it briefly at some point, but it's not a part of my project. Okay, the language in which these axioms are formulated is a language that's solely formulated with logical symbols, of course, the logical symbols of second-order logic, then the primitive membership symbol, and I also use a primitive set predicate, okay? In a context where it's clear that we're only dealing with sets, you could drop that, right? So for example, if you open up Stuart Shapiro's book on second-order logic, Foundations Without Foundationalisms, and you go to the page where he presents the second-order Zermelo-Fraenkel axioms of set theory, he doesn't use a set predicate, because it's understood that all the quantifiers, the first-order quantifiers are ranging over sets, right? And the second-order quantifiers are ranging over properties and relations of sets and so on, okay? But, you know, personally, I think of these axioms in the way that all the quantifiers are bounded, are restricted by a set predicate, okay? So that's why I use it here, okay? And the membership, the primitive membership predicate is what you think, right? Intuitively, it should express the membership of a set being a member of another set, okay? Now, the theory has certain salient properties, okay? One I already mentioned, almost all pure mathematical theorems as we have them now in mathematics are known to be derivable from these axioms and, of course, auxiliary definitions in the deductive system of second-order logic with comprehension, right? With extensionality for second-order entities and with the axiom of choice, okay? So comprehension, I hope, is clear, right? Second-order logic includes comprehension, of course, comprehension axiom scheme. Then extensionality, right? By that, I mean the extensionality, say, for example, for second-order properties, okay? And once I postulate extensionality for them, okay, by the corresponding second-order axiom, I can think of properties as extensional properties, if you like, as classes of entities. Here, in my case, classes of sets and so on, right? And in fact, I will presuppose extensionality in that sense, okay? And then there is the axiom of choice, where in this context, I want to think of the axiom of choice as a logical axiom, okay? So for me, it belongs to the logical part, okay? Not to the eigenaxioms, as it were, of second-order set theory, okay? So, you know, we can talk about it if you're worried about that move. I'm not worried about it at all. I'm just dealing with classical mathematics here, classical set theory. So choice will be presupposed. And once you do it on a second order level, you can think of choice as a logical principle. Okay, we can talk about it later if you're interested, but I'm presupposing that here. Okay. Now, second order set theory in that sense is known to be a non-conservative extension of first order set FC. Okay. It, like ZFC, it captures the cumulative hierarchy, right? So within the theory, you can define your V0, right? And when you have defined V alpha, sort of by transfinite recursion, you can define V alpha plus 1, and you can define V lambda by taking unions and so on. So you build up in all these stages the cumulative hierarchy such that what you find in these stages is the sets, and every set can be found in one of these stages ranked by set theoretic ordinals, right? So that's our nice cumulative picture that we get in first order set theory, and of course we get in second order set theory as well. What we get in second order set theory, what we do not get in first order set FC is almost categoricity, right? So the second order Zermelo-Fraenkel axioms of set theory pin down the structure of the cumulative hierarchy uniquely up to sort of, you know, the height of the hierarchy, right? It's clear that the height must be some strongly inaccessible ordinal, right? But the only thing that's left open is sort of what that ordinal is, how high up the hierarchy goes. But other than that, the structure of the set theoretic hierarchy is pinned down, right? As shown essentially by Zermelo back then, right? And that's nice because if you presuppose the axioms and sort of, you know, you buy into the second order machinery, you can think of these Zermelo-Fraenkel axioms of second order set theory as giving you almost a categorical axiomatization of the cumulative hierarchy. Okay, and that's nice to have, and that's something that you do not get in that form in the first order case. Okay, now why is that useful for me? Because whatever, you know, the membership symbol might have meant to you antecedently, whatever the set predicate might have meant to you antecedently, from now on, and this will be the point then of building my logicist framework, I want you to think of the second order Zermelo-Fraenkel axioms of set theory as implicitly defining the concepts expressed by the membership symbol and the set predicate, okay? I want you to think of membership and sethood as sort of being given by that axiomatic theory, right? They become theoretical concepts that are sort of determined maybe only to some extent, but still constrained, right, by the axioms of Zermelo-Fraenkel set theory, right? And since, you know, second order set theory gives us the cumulative hierarchy and is almost categorical, what we can think of in that way is we can think of, you know, membership and sethood as being given by a theory that more or less captures the iterative conception of sets as we have it. Okay, so whatever membership is, it is characterized now by the second order axioms that I've just mentioned. That would be the idea. Okay. Now, how can we make this idea and this talk of implicit definition more explicit? Because that is my first step of my logicism. Okay. And now the idea will be a familiar one from different areas of mathematics where people are dealing with what is sometimes called Ramsification. Okay, and I'm now explaining what that is, but I will do so on very Carnapian grounds as I will explain in a sec. Okay, so the first step to get there is you take the axioms of second order set theory that I've just mentioned, and you replace the membership symbol in them by a binary relation variable R, and you replace the unary predicate, the primitive, right, a set predicate, by a unary class variable, or if you like, extensional property variable S. Okay, so then we get an open formula. ZF2 of R and S is now an open formula where R has taken the place of the membership symbol and S is taking the place of the set predicate. Okay, but now it's an open formula. And what is nice about that open formula is sort of it captures, as it were, the abstract conceptual roles that membership and set occupied within this axiomatization of set theory. Okay, what's left in this open formula ZF2 of R and S is just logical symbols. Okay, sort of the logical structure is left, right? But other than that, you know, different entities, if you want, different concepts can now occupy the R role and the S role, the role that, you know, membership and set played in the original axiomatization. And this open formula can now help us to define membership and sethood through their conceptual roles, as it were. Okay, I will use that open formula and plug it into an explicit definition of membership and sethood. Okay, and the way I do that is I do so by invoking a logical gadget, you know, a new logical operator, which is well known as well, and that is David Hilbert's epsilon operator. Okay. So intuitively, you should think of the epsilon operator as something like the more known, the better known iota operator, right? A iota operator sort of formalizes the X or the R such that, right? So we try to denote, to refer to an entity by describing it, okay? And by hopefully, if things go well, by describing it uniquely. That's why in natural language talk, we would use a definite article, the X or the R such that, right? And formalized, we get using Russell's iota term, iota X or iota R, and then we have sort of a describing clause, right? So this is these terms, the iota terms, we would now often call definite descriptions, right? And there is a logic for it and different kinds of semantics for it and so on and so forth, right? And now the epsilon operator is just like the iota operator, but we do not want to presuppose uniqueness. Okay, that is why in natural language terms, we would read epsilon X or epsilon R not as the X or the R such that so-and-so is the case, but rather we would say NX or NR such that blah, blah, blah is the case. We would use an indefinite article, A or N, rather than the definite article the, okay? Now, but other than that, sort of syntactically, these epsilon terms behave very much like, you know, iota terms, right? So, you know, what I'm going to do later in my logicist framework, I'll have an object language and also a meta language, and in both of them, syntactically, I will have epsilon terms available. Epsilon X such that, and then there comes a formula saying, you know, sort of constraining the X, or epsilon R such that so-and-so, there comes a formula, and it's meant to constrain the R, okay? That's the idea. And if there is no unique X or unique Y that satisfies sort of the body clause, then that's not a problem. It would be a problem for the iota operator, then we would have to deal with that, but it's not meant to be a problem for an epsilon operator. If there is more than one X that satisfies the clause or more than one R that satisfies the clause, then the idea is that the epsilon operator is meant to pick, to choose, to select one of the candidates that satisfy the describing clause, okay? It's meant to pick one of the x's such that so-and-so is the case, or one of the r's such that so-and-so is the case, right? And that's why it's not a problem if there's more than one, because the epsilon operator is understood to pick one of them. Okay, and this gets reflected also in the corresponding logic of the epsilon operator, to which I will turn on the next slide. But before I do so, let me first show how I'm going to use these epsilon operators and epsilon terms to get my intended definition of membership and sethood. And I'll present the definition in two versions. Mostly I'm going to focus on the first version, but the second version is another one that you might like maybe for different reasons, okay? So the first definition goes like this. I will define membership, that's the second order definition as it were, right, as an R, okay, a relation R if you like, such that there is an S, such that R and S together jointly satisfy, as it were, the axioms of second order Zermelo-Fraenkel set theory. And it is here where I'm using this open formula ZF2 of R and S that I've explained on the previous slide. Okay, so basically I define membership to be a relation such that, right, you know, there is an underlying domain, as it were, such that the relational domains together are such that the structure of the cumulative hierarchy is preserved, roughly speaking. Okay, and then I can define sethood as, you know, X is a set just in case it's a member of something. Okay, remember, the only things that can be members here will be sets anyway, not Ur-elements, because I'm going to do just pure set theory. Okay. In fact, I could also define set differently as an epsilon term if I wanted, or even as a iota term, because the way I'm thinking of set F2 here is such that once membership is fixed, sethood will be fixed. Because in fact, I will assume in set F2 a little additional axiom that basically says sets are precisely the things that occur as arguments of the membership relation. Okay, and that's why you get membership sort of for free. You get sethood for free once you have got membership. Membership I get through an epsilon term, and then I get sethood from that, as it were. And membership here, that's the epsilon that I've just defined here, right? So that's not your, you know, whatever you understood by membership antecedently, but it's the one that we've just defined using this epsilon term. Okay, and the second version is like the other version. It's just that here I additionally say that everything sort of in the underlying domain of set theory will be a logical object, okay? And the predicate that I'm using here, logical in C, okay, that will be in my logicist object language, in my logicist meta language, another primitive, but I'm going to think of that primitive as a logical primitive. I will have to say more about this soon. So there will be another, as it were, logical term in an extended sense, by which in my logicist framework, I will be able to distinguish logical objects in my domain from non-logical objects, right? So for example, if I add, you know, physics to my logicist framework, I might want to describe physical objects in space-time with causal powers and so on, okay? And I want to distinguish these physical entities from my logical entities. And for that purpose, it might be useful to have this logical in C, that's the framework, the logicist framework, predicate, and I'm thinking of that as a logical term. And what that definition does is it makes explicit that the sets that we will get out through the logicism will be these sets will be sort of logical objects in our logicist framework. This is stated explicitly here, whereas here it's, if anything, left implicit. Okay, and that might be an advantage to the second version. But other than that, for me, the versions are sort of on par. And mostly, as I said, I will focus on the first version because it's simpler. Okay, now about epsilon terms. So as you might know, the Hilbert school, right, the Göttingen school, used these epsilon terms for very different purposes, for which I'm using them here. They use them as part of sort of, you know, working out Hilbert's formalism or Hilbert's program, right? To maybe get a better handle on consistency or conservativeness proofs and the like, okay? But epsilon terms can also be used for other purposes. And famously, Carnap suggested in the 1950s and then in the 1960s and 70s to use higher order, especially second order epsilon terms, to define explicitly theoretical terms in science, right? For example, say, the concept of electron in physics, right? It's a theoretical term. You might think of it as being given maybe by some theory, And Carnap suggested to make this implicit definition, as it were, of electronhood in that theory explicit by determining the property of being an electron through a higher order epsilon term, right? Much in the way as I do it here. In his case, he would have used some axioms of physics. I'm using some axioms of mathematics because I'm interested in logicism here. Okay? You might also think, why not use a iota term here? Couldn't I have said VR such that blah, blah, blah instead of NR? So why not use a iota term rather than an epsilon term? There is another famous paper from 1970, not by Carnap, but by David Lewis. It's called How to Define Theoretical Terms, which appeared in the Journal of Philosophy back then, where he started from Carnap, but then replaced the epsilon terms by iota terms. Okay? I'm glossing over details here. So Lewis did it all in the first order language, right? But he could have also done it in the second order language, okay? And then basically it would be what I have here, but it's with a iota instead of an R, roughly speaking, okay? Now, in physics or in empirical sciences, what Lewis suggested using the epsilon terms might work, okay? So this is open to debate. Because you might hope that with a little luck, sort of, physics, maybe with additional assumptions, we'll be able to pin down our physical concepts uniquely, and then the iota terms would work, right? It's just that in a mathematical context, right? As far as I'm concerned, this would be a no-starter, right? Because uniqueness for all the interesting cases will not be satisfied in mathematics, right? Think of it in the way that once you have some interesting enough mathematical structure on some first order domain, right? Then you can permute the first order individuals, right? And get something that is not a structure that's sort of not identical, numerically identical, but just isomorphic. You get lots of isomorphic copies, as it were, right? So roughly, if there is one system that satisfies your axioms, there will be another one, an isomorphic one, but still a different one that also satisfies the axioms, okay? And then we wouldn't get uniqueness as we would need it for the iota terms. Again, this will not be a problem for an epsilon term, because if we get lots of isomorphic copies, right, or almost isomorphic copies, then the epsilon term will just pick one of them, and that's good enough for my purposes, okay? Now, what Carnap also liked about the epsilon term reconstruction of theoretical concept is that he thought epsilon terms have something open-ended about them, right? So, for example, you could define a theoretical concept by an epsilon term, a higher order epsilon term, and then maybe a bit later in science, scientists might add further axioms, okay, which you might then, in another reconstruction, put into the describing clause, okay, and you get in your rational reconstruction, your explicit definition, then a new updated epsilon term, right? And, you couldn't derive that the old epsilon term for your theory, right, would pick the same object as the new epsilon term for the updated, for the revised theory. You couldn't derive that. But it would be consistent with all assumptions that they, in fact, would pick the same object, right? So the equality, as it were, the identity statement between the old epsilon term and the new epsilon term, right? This equality statement, you might just as well assume to be true, and it wouldn't be inconsistent with any of your background assumptions, right? Because an epsilon term can live with sort of underspecification, right? It picks one of the candidates, and then if you continue to narrow down what is described, if you add constraints, right, and you pick something that satisfies the added constraints by another epsilon term, right, the object you pick might just as well be amongst those that were, might just be one of those that was picked by the old epsilon term, right? Which nicely, Carnap argued, reflected sort of the open-endedness that concepts might have in science, right? Where part of scientific progress is not just that we gain more knowledge about the world, but that we might also, update our scientific concepts, as it were. And the epsilon terms would be consistent with that, okay? In my set theoretic concepts, I think the definition of membership and sethood, as it were, indirectly, through an epsilon term, nicely reflects the inexhaustibility of the concepts of set and membership that people like Gödel in his Gibbs lecture argued for, right? So if we are never done with set theory, right? We might never be done with getting a full handle on the concept of set and membership, as it were, okay? And that shows up in the epsilon term definition that I'm using here, okay? Now, my definitions do not really care what gets picked by the epsilon term. So long as what gets picked satisfies, of course, the defining clause, which, except for that existential quantifier, is just sort of the open formula that we got from our second order axioms of set theory. Okay, so my logicism doesn't think of it in a way that there is a uniquely determined membership relation or so, right? That's the intended model, as it were. And now we want to capture it somehow. That's not part of the logicism that I'm developing, right? Rather, as long as you give me something that satisfies the right axiom, I'm happy with it. Okay. So my logicism is consistent with thinking of the membership predicate as being semantically indeterminate, right? As the second order axioms of set theory not pinning down sort of membership uniquely. And in fact, I don't think it pins down membership uniquely. Think of the different inaccessible heights that set theory can have, right? So, as long as there is enough structure, I'm happy with it. Okay, that's basically what my logicism conceptually will give you. Okay. Now, as far as the logic of epsilon terms are concerned, this is part of the logic of the epsilon term. I hope you're seeing where I'm pointing here, right? The first axiom, right? So this is part of what logicians would call the epsilon calculus, right? If there is an R such that phi of R, then epsilon R phi of R picks one of these R's, and hence phi of epsilon R phi of R will be the case, right? Now, this logical axiom does not say anything about the case when the antecedent is wrong, is false, right? If the antecedent is false, then anything could be picked by the epsilon term, right? But as long as there is something that describes satisfies the defining clause, the epsilon term will pick one of these things, okay? And that's what's expressed here by the axiom of the epsilon calculus. We could also add extensionality as an axiom for the epsilon calculus, but it won't be important for what I'm talking about today. But you can always add it, and it will make your theory more convenient. Okay. Now, by the logic of the epsilon operator that I've just described, this is a particular logical axiom, and it will be a particular logical axiom, for example, in the object language of my logicist framework. Okay. So here I've used as the phi of R. There is an R such that set f2 R of S, right? That's my phi of R. Okay, and then by using that phi of R, I get as an instant of that scheme this axiom here. Okay, this will now be a logical axiom. Okay, and now you can see in this logical axiom, in the consequent, I have this epsilon term, but this epsilon term is precisely what we define the membership relation by in the first definition. And I'm focusing now on the first definition on the previous slide. So by substitution of identicals through definition, we can replace that epsilon term by the membership symbol here, okay? And then I say here there is an S, but I already told you, right? The way I set up things is S will always be determined once membership has been determined. Well, membership has been determined through the definition, so we get actually a unique S, and that's the set property, as it were, right? The set class, because I'm extensional. So I can actually put here set, and I get that a derivation of this if-then statement, from the definition that I had on the previous slide and substitution of identicals. So this means this conditional in Frege terms will be analytic. It's Frege analytic, right? It's derivable in the deductive system of second order logic from the definitions that I'm using and logic, of course, right? So this conditional I'm going to call C for the rest of my talk. And it corresponds to what people in the literature would call a Carnap sentence, okay? Especially if you're interested sort of into general philosophy of science, and you think that theoretical terms are definable, right, from theories, these people will talk about a Carnap sentence, and they mean a conditional like that. Of course, they might use empirical theories where I use second order set theory, but independently, okay? And that's also a conditional that Carnap very much focused on when he was dealing with theoretical terms. Of course, he was a modest person, right? He didn't call it the Carnap sentence, but we call it now the Carnap sentence because he was the one to introduce that, okay? But now look, so what I just said was this conditional will be analytic in the logicist framework that I will be building in the next part, okay? But additionally, right, assume we also had that the antecedent, which is this existence claim here, say we also had that this existence claim would be analytic, right? Then we would have the existence claim is analytic. We would have if existence claim, then second order set theory is analytic. And it will follow from the definition of analyticity in the logicist framework that analyticity will be closed under logic. So if this antecedent is analytic and the conditional is analytic, it's going to follow that also the consequent will be analytic. And now analyticity is not meaning Frege analyticity, but Carnapian semantic analyticity in the logicist framework. And what that is, I'm going to explain very soon. Okay, but it will also be the case that everything that's Frege analytic, that follows logically sort of from definitions, will automatically also be Carnap analytic, semantically analytic. Okay, so what we get is, if the antecedent here, if this existence statement were analytic, we would get in the logicist framework the analyticity of the axioms of second order set theory. And by that, we would get the analyticity of, all standard mathematics as explained before. Okay, so the main question for much of the remainder of my talk will be, is this higher order existence claim analytic or not? And I'm going to argue, yes, it's analytic in the logicist framework that I will be building. Okay, I call this higher order existence claim R, where R is for Ramsey sentence. And again, there's something in this literature on theoretical concepts in science where people are not just dealing with the Carnap sentence, but also with the Ramsey sentence. And what they mean by that is an existence claim like that. Okay, again, they would have an empirical scientific theory here. I have set theory here, but other than that, it's the same idea. And it's called the Ramsey sentence because Ramsey already had an idea like that, and Carnap was picking up that idea later and so on. Okay, so that's where this terminology comes from. So what's crucial in my approach is that there is the definition of membership and sethood. We get that by the epsilon term. And then from the definition and logic, we get the Carnap sentence, which is a conditional. Okay, what we do not get in this way is the Ramsey sentence. But, if the Ramsey sentence is also analytic, then the whole package will deliver the analyticity of standard pure mathematics. And that's the plan. Okay, I hope so far the plan at least is clear. Okay, now before I turn to this analyticity of the Ramsey sentence, which is of course controversial, let me deal with sort of the other part, right? The Carnap sentence and my explicit definition of membership a bit more. Okay, so first of all, as I said, Carnap's theory of theoretical terms used exactly conditionals like that, the Carnap sentence, and existence claims like that, the Ramsey sentence. Now, when he was reconstructing sort of theoretical terms in empirical sciences, okay, Carnap would argue, like I did, the Carnap sentence to be analytic. So that's like what I had before. But in his case of empirical theories in science, the Ramsey sentence of a theory, this kind of existence claim, would typically be synthetic for Carnap. Okay, so it would not be analytic; it would be synthetic. Okay, however, my goal is not a reconstruction of, relativity theory. My goal is a reconstruction of pure mathematics, right? And pure mathematics, I want to argue, being a logicist here, can be reconstructed such that its Ramsey sentence is analytic and not synthetic. And that's why I'm going to argue for the analyticity of the Ramsey sentence and not for its syntheticity, okay? Syntheticity would just be the negation of analyticity in that context, okay? But I want to argue that the Ramsey sentence is analytic. Semantically analytic in the logicist framework, as I'm going to explain so, okay? So just that you make the right connection to that kind of literature if you know about it, okay? Now, notice that once I have these definitions implemented in a suitable logicist framework, this will be this framework C that will be explained very soon, we will have a strong argument for the first thesis, right? Because the first thesis said all mathematical terms in standard mathematics, and that really meant all mathematical terms in second order set theory, are explicitly defined from logical terms in the logicist framework. Okay, and once the logicist framework will be built such that I've built these definitions into it, we will get that result, right? Because look at what the definitions do, right? The mathematical terms in second order set theory, right, are really just two, namely the membership symbol and the set symbol. Right? Everything else, all other mathematical terms will be defined in terms of them. So if I'm able to define them in logical terms, I will be able to define all mathematical terms in logical terms. That was the idea. And now I have defined, I want to claim, membership and sethood in purely logical terms in this way. Because look, for example, at this epsilon term in the first version of the definition of membership. I want to argue that this epsilon term is a purely logical term. It only consists of logical symbols, right? Because the only symbols that occur there are, of course, the symbols of pure second order logic, and they are logical, right? So if you worry about that, maybe for all on the second order quantifier level is not logical for you. Let's talk about it later. But for me, it's a perfectly logical symbol. And I want to say that most philosophers of these days would agree, okay? The only other symbol that occurs here, other than what second order logic gives you, is the membership symbol. And so you might worry, is it really a logical symbol or not? And I want to claim it's a logical symbol, okay? So the epsilon operator for me is a logical symbol, and the concept it expresses is a logical concept, okay? And one way to see this is that the epsilon operator is very, very, very closely related to the existential quantifier, right? So for example, people like Hilbert and Bernays or so, they showed that you can even define the existential quantifier in terms of the epsilon operator, right? So if you think that, you know, the existential operator is logical, you better think that the membership, the epsilon operator is logical, okay? And there's also a nice paper by Jack Woods where he argues explicitly for the logicality of the epsilon symbol. So I'm going to use that, okay? So it's logical. Okay. Now, in the second version, I also have this new primitive term logical in the framework. Okay. And I want to argue that it's at least logical in a slightly extended sense. Okay. Like in the sense in which we want to say, well, you know, we have the truth values, right? In classical logic, true or false, right? Or Frege would have had the true or the false, right? Truth, falsity. And accordingly, the notion of truth value is a logical notion, okay? Or, you know, we might define sort of meta-logically, as it were, logical truth, okay? And then think of the concept of logical truth as itself a logical concept, maybe in a slightly extended meta sense, but still, right? Or think of provability logic, right? Where you have a provability operator. You would use the same provability operator to express the provability of, you know, some arithmetical claim, right? As you would use in provability logic, the probability of some arithmetical claim, right? Although sort of the outer occurrence of the probability operator is a sort of, as it were, meta probability operator. But we still think of it as a logical concept, as it were, logical operator in probability logic, right? And in the same sense, I want to understand logicality in the framework as another logical expression, okay, primitive logical term that is in the logical vocabulary of the conceptual framework that I'm having. And hence, again, we have this even in the slightly extended epsilon term, just logical terms. And so we get a reduction, a conceptual reduction of membership, and then indirectly sethood to logical terms, okay? So, you know, with that in place, with these definitions in place, I will have argued for the first logicist thesis that I had, right? Once I've written that into my logicist framework. Okay, I hope that was clear enough how you get this first part of logicism. Okay, basically it uses these epsilon terms, but that's pretty much all that you need, and you know, higher order languages. Okay, now one final point about that, and then I'm turning to the conceptual framework and to semantic analyticity. Now, even independently of my forthcoming argument for the analyticity of my Ramsey sentence R, this higher order existence claim, the definitions, these two versions, right, of membership and sethood, by themselves already, I want to say, argue to a decent form of logicism, okay? So already now we have a kind of logicism that is not that bad, and that is what I want to explain as a final bit of information here before I move on, okay? Now, we've already seen that we can logically derive from these definitions of membership and sethood, we can logically derive from them the Carnap sentence. So this was this conditional, right? So, you know, roughly it says if Ramsey sentence, this higher existence claim, then we get, you know, this longish conjunction that are the axioms of second order set theory. And additionally, it's well known, right, that from these axioms of second order set theory, we can derive in the deductive system of second order logic and from auxiliary definitions all the standard theorems of pure mathematics. That's what I just mentioned before. So for example, take the fundamental theorem of the calculus, right? So say you're in your analysis 1 lecture and you prove FTC, this fundamental theorem, then you might think of it in a way that you prove it actually from the axioms of second order set theory plus auxiliary definitions, right? Of continuity and, you know, integral and real number and what you need, okay? Now, by the deduction theorem, that means you can just logically derive in a deductive system of second order logic from these auxiliary definitions, this conditional here, where the antecedent is just the axioms of second-order set theory, and the consequent is the standard theorem of pure mathematics, namely FTC, the fundamental theorem of the calculus, right? So from logic and definitions, we get this conditional, and from logic and other definitions, we get this conditional, right? But if you put them together, what this means is that just from logic alone, you can logically derive from the definitions put together, my definitions of membership and sethood, and the auxiliary definitions, we get if Ramsey sentence, then FTC, right? Because here we have if A then B, and here we have if B then C, right? So, by logic, we get if A then C, which is this conditional here, okay? Which means that by logic and definitions, we cannot quite logically derive, the standard theorems of pure mathematics. That wouldn't work. But what we can derive is we can sort of derive the standard theorems of mathematics in this conditional form, where they occur as a consequent here, and the antecedent is the Ramsey sentence, right? And this doesn't just work for FTC, but for every, standard mathematical theorem that we've already proven in 2025, right, of pure mathematics, okay? And we can derive that just by logic, right, from definitions. So which means all these conditionals are Frege analytic, which is going to mean all of them are Carnap analytic, right? So we don't get the semantic analyticity of pure mathematics, but we get the semantic analyticity of theorems of pure mathematics as consequence of these conditionals where the Ramsey sentence is in the antecedent. This amounts to a weaker logicism than the one that I want to argue for, but it's still a sort of logicism. It's a kind of logicist if-thenism or deductivism, as Russell presented it early in his work on mathematics, right? And it is similar very much to how the axiom of choice and the axiom of infinity was treated in Whitehead and Russell's Principia Mathematica, and also how choice and infinity was treated by Carnap when he was presenting his version of the simple theory of types, which he did in a little book called The Abriss der Logistik in 1929. Okay? So what I mean by that is, it is sometimes said that Whitehead and Russell's logicism in Principia Mathematica relied on the axiom of choice and the axiom of infinity, which was bad because, some people might worry about the logicality of choice, and even more people might worry about the logicality of the axiom of infinity, right? So they might think that's where Whitehead and Russell's logicism failed, actually, right? Because they postulated the axiom of infinity, you get infinitely many objects, right? At least at the first order level, at least maybe even at every order, okay? But it's not a logical axiom, so that's where the problem was. But if you read Principia Mathematica, then you are going to see that this is not actually what Whitehead and Russell are doing. Rather, they're suggesting to use the axiom of infinity, and they do the same for the axiom of choice, as an antecedent where the consequent will be some interesting theorem of mathematics, and they will show that the full conditional, right, with, say, infinity in the antecedent, can then be derived from their, ramified type theory. So they proceed precisely in the way that I'm presenting it here, okay? And Carnap did the same thing with his simple type theory, and many people do with simple type theory, okay? So actually, this version of logicism that we get just from the two definitions with the epsilon term is actually, not a bad logicism at all. It doesn't quite give you the full thesis with part 1 and part 2 that I presented, but it already gives you a weak but still interesting form of logicism, okay? All right, but now, finally, let me turn to the Ramsey sentence, okay? And then I'll wrap up, okay? So the Ramsey sentence was this existential higher order, second order existential claim, okay? Now, it's obvious to see that this statement also consists just of logical symbols, right? So if it's also true, it will be logical and true. That's already nice, right? Notice it will not mean that this existence claim is logically true in our standard modern Tarskian sense. In fact, it's not, right? Because there are countermodels to it. Right? So, for example, it's very easy to see, obvious, right? Set theory in the background, that this can only be satisfied in an infinite second order model, right? Where there are infinitely many individual sets, right? So every finite second order model will already make this Ramsey sentence false, which means the Ramsey sentence is not logically true in our modern sense, okay? So, in fact, accordingly, I will not argue for the logical truth of the Ramsey sentence, right? Although it's logical and true. What I want to argue is that it's still analytic, or at least probably analytic in a suitable logicist framework, which is something else, okay? Now, at this point, you might worry, okay, I see the strategy, but it's hopeless to argue for the analyticity of an existence claim because we all know that existence claims cannot be analytic, right? And for example, for someone like Kant, right, this might well have been true, okay? But if you have an extended, a modernized version of analyticity, this might not be true, okay? So, for example, Frege thought that existence claims can be analytic, okay? And accordingly, Carnap thought that depending on what the conceptual framework is like, existence claim, may well turn out to be analytic. It wasn't a problem for him at all. Okay, and he is totally explicit about that. For example, in his famous paper on empiricism, semantics, and ontology, which you might know, where he says, in this and that arithmetical framework, the existence of the number 5, there is an x such that x equals 5, right, is analytic. Or in the same framework, the existence of prime numbers greater than 100 is analytic, and so on, right? So for him, it was perfectly fine that existence claims turn out to be analytic. Okay, that's not a problem for him. Okay, and the notion of analyticity that I'm going to use, okay, will be such that existence claims in principle can be analytic. The question is then just, is that an existence claim that will be analytic or not, right? The idea is not that every existence claim is analytic, just that there are some existence claims that are analytic. And then the question that I'm interested in is this one of them, okay? Now, for Carnap, all of that depended on a conceptual framework, okay? And the same will happen here. So I will have to tell you more about the conceptual framework that I will use for my logicism. Okay, and I'll turn to that. Okay, now Carnap himself didn't actually use the term conceptual framework, but in his early work he would just talk of languages, right, or linguistic frameworks. And then once he had done semantics, he would talk of intentionally interpreted languages or semantical systems. And that's pretty much what I mean by a conceptual framework as well. Okay, so a framework, okay, is more than just a language in a syntactic sense, right? It comes with interpretation mappings, as it were. It comes with semantics. Okay, so don't think my conceptual framework is just something syntactical. That's not the case. Okay, and it wasn't the case either for Carnap when he was dealing with semantics. Okay, now what's the philosophical idea here? Okay, so I just told you that for Carnap it was fine that existence claims would turn out to be analytic in certain frameworks, but you might think that's just a biographical comment on Carnap. But why would it make philosophical sense to think so? And let me now tell you what the background idea is as far as Carnap is concerned, but also as far as my logicism is concerned. Okay, the idea of a conceptual framework for Carnap is that it's meant to organize information by structuring it in a particular manner. Okay? So, a conceptual framework will not be like a scientific theory that tells you something substantial about what the empirical world is like, but rather it takes, as it were, any scientific theory you give it, and it organizes organizes the information in that theory in a particular manner, right? If you change the framework, and you can do that, then you will organize maybe the same empirical body of knowledge in a different manner, okay? So a conceptual framework is much like, different textbooks in mathematics, where maybe the same body of mathematical knowledge, say about the real numbers, is organized in different ways. And we all know from mathematics, right, that mathematical textbooks sort of organize the mathematical area they are dealing with in different manners, right? What's the definition here in one textbook might not be a definition there in the other textbook and like. And the same holds for conceptual frameworks in Carnap's sense, okay? And once information has been organized in a conceptual framework, this information can then be expressed linguistically by sentences of an object language that gets interpreted in the framework. So all these conceptual frameworks for Carnap come with an interpreted object language that gets interpreted by the framework or by the semantic systems, as it were. That is the framework. Okay. Now, in some ways, personally, I think of these Carnapian frameworks as taking over some of the information structuring role that space and time had for Kant, if you read the Critique of Pure Reason. Okay, so for me, that's also part of the background of the logical empiricists. Okay, so Kant thought of it that space and time, as given to us, sort of organizes information about the empirical world in a particular manner, in a temporal way, in a spatial way, and so on. Okay, and Carnap thinks of his framework as organizing information in a similar manner. But there are also crucial differences, right? So Kant would then say, we need empirical intuition, right? Or maybe pure math, right? Anschauung, okay, to get hold of that information. That's not the case for Carnap, right? Intuition in that Carnapian sense doesn't play a role for Carnap, right? Rather, it's all about sentences expressing propositions or predicates expressing concepts in the framework, right? That's the access. It's a kind of semantic access, right? A linguistic access. Secondly, for Carnap, there's a whole plurality of frameworks available that we can all make precise, okay? And, if we're not happy with the framework that we're using, we can revise it and use a different one, right? That's not the case for Kant, right? Because space and time are just given to us as rational subject, and that's it, right? You can't revise it, and there's no pluralism, right? And finally, for Kant, right, the space and time that I was just mentioning just is physical space and physical time, right? But not, of course, the conceptual framework for Carnap. For conceptual framework for Carnap does not tell us what the empirical world is like, right? It's independent of the empirical world, right? It's compatible with lots and lots and lots of different theories, substantial theories about what the empirical world is like, right? It just organizes the information that would be contained in these theories in a particular manner, right? So for a typical empirical sentence, right? Say you do physics now in your logicist framework of mathematics because you need math in science, right? You might wonder as an empirical scientist, is the empirical physical law A true or its negation, right? And Carnap would say, as a logical empiricist, well, you need empirical methods to determine that, right? It's not to be determined by the framework, right? But at the same time, Carnap was also a logical empiricist, right? With a heavy emphasis also on logical. So what Carnap thought was that both A, this empirical law, right, and not A, understood in the framework, share some kind of abstract conceptual and propositional structure, right? What you find in the A, that's in the A and also in the not A, as a part at least, right? That needs to be in place prior to empirical investigation, right? Roughly, you need to understand A and not A before you can ask the question, is A or not A true, and argue for that on empirical grounds by experiment and observation and whatnot, okay? Maybe by induction and the like, okay? But the conceptual and propositional structure by which we understand the sentences A and not A needs to be there. And that is why, the conceptual framework itself needs to come with ontological commitment, namely to that abstract structure thought. That is why, okay? And what Carnapian Logicism, in the way that I suggest it, right, it suggests to rationally reconstruct mathematics as dealing with precisely the abstract structure that is provided by the conceptual framework itself, okay? And part of this abstract structure, if you then look at sentences, right, makes certain existence claims true. Existence claims that track the existence of that abstract structure that is provided by the framework itself, right? And that is why these existence claims, like the Ramsey sentence, will come out as analytic in the framework. Like A or not A will turn out to be analytic in the logicist framework that I will now deal with. Like definition 1 of membership will turn out to be analytic in the framework, right? All of them will be analytic, but especially also the Ramsey sentence, because it tracks the commitment that the framework has, because it gives you the conceptual and propositional resources to even grasp, as it were, these kind of thoughts, whether A or not A is true. Okay, so all of these sentences, including the Ramsey sentence, will be semantically analytic in the framework because they come with the framework, as it were, right? In which then we might end up doing empirical science or so, okay? So that, I think, is a good philosophical rationale for even count, certain existence claims as analytic, right? So it's not just an oddity that Carnap thought they could be analytic, right? There's, I think, a good information, philosophical reason for doing so, okay? Now about analyticity, right? In his later work, where he's doing semantics, he would define analyticity pretty much in the way that I do now in my logicist framework, okay? So roughly, and I have some quotes here, right? He would say, sometimes he would say L truth or A truth, but what this means really is analyticity, and he says that, okay? So he would say a sentence in a semantical system, in my case a framework, will be logically true or L true, right? If it's true in a way such that the truth can be established just on the basis of the semantical rules of the system. Okay, so it's sort of truth in virtue of the semantical rules. That is what analyticity is for him from the 1940s. Okay, roughly speaking. Okay, one way of making that more precise, which Carnap also uses in part of his work, is to say, and I will going to express that in modern terms in this way: every framework comes with a class of what I call semantically possible worlds, okay? And these are sort of ways the world might be where the only thing that you hold fixed is the semantical rules of the framework, right? So we all now like to seek in philosophy of metaphysically possible worlds. And these are ways the world might be when we hold the metaphysical laws fixed. That's not what I'm dealing with here, okay? But semantically possible worlds in the framework will be the possible worlds, the ways the world might be, right? Where we hold the semantic rules fixed, okay? We throw all the worlds in there, right? As many as possible, all the combinatorial possibilities, so long as what we throw in there satisfies the semantical rules of the conceptual framework that we're interested in. That's the idea, okay? So if you read Meaning and Necessity by Carnap, you find the definition that a sentence is L true, analytic in my sense, semantic analytic, if the sentence holds in every state description, okay? And in earlier work, before Meaning and Necessity, namely in Carnap's Introduction to Semantics, he has the same idea, but there he doesn't use state descriptions, which are syntactic entities, but something that he would describe in a higher order language. And what he describes in a higher order language is very much what we would now call a model, okay? It's just that he describes these models in the language of higher order logic, type theory, whereas we would now typically describe them in first order set theory, right? When we do model theory these days in logic, okay? So, he has different versions in different work, but I want to say that he always has the idea that there is a conceptual framework, it has semantic rules, and it comes with a class of what I now call semantically possible worlds, which are ways the world might be that are sort of compatible with the semantic rules, okay? In part of his work, he calls them state descriptions, which are syntactic entities. In other part of his works, he calls them differently L states, and he has different terms for that, and describes them sort of very much like we describe now models, but in a higher order language, okay? But it's the same idea, okay? Now, I will follow Carnap in describing these worlds or models in the language of higher order logic, not in the language of first order set theory. Okay, so you can think of these semantically possible worlds that come with the framework as like models with a domain and relations that come on it, and what you need, right? But I will describe them in higher order logic rather than in set theory. Okay, and now analyticity in that semantic sense, okay, then depends very much on what the space of semantically possible worlds is in the framework, and that very much depends on the framework. If you change the framework, you might change the space of semantically possible worlds, and thereby a sentence that comes out as analytic in the one framework might not be analytic in the other framework. And that is exactly what Carnap intends. Okay? So this is part of the game. Analyticity is relative to frameworks, according to this sense. Okay? And this is very much like, Tarski had truth in L, as it were, right? And he didn't give a truth definition for all languages whatsoever, right? But, Tarski just gave a scheme of how to state the truth definition, right? Truth in an object language relative to a meta language, as it were, right? And all of that needs to be determined and plays a role, right? And what Carnap does in terms of his semantic system, or what I call conceptual framework, is exactly like that, okay? It's sort of analytic in the framework that you get, okay? Like Tarski had truth in L. Okay. Now, the logicist framework that I'm putting forward has an object language and a meta language part, okay? The object language is a second order language, has the resources of second order logic, has an epsilon term, has this logical in the framework predicate that I mentioned before, which I regard as part of the logical vocabulary. And then you might throw in some descriptive terms if you like, just for fun, just for illustration. And what I throw in here as descriptive terms is bachelor, man, and married, right? And you get the idea why that is, because bachelors will turn out to be unmarried men, okay? That's the idea. These are unary predicates. Of course, intuitively, we think of them as applying to empirical entities, namely human beings, right? And so on. They have nothing to do with logicism. This is just for illustration, okay? Just that you see, like, there could also be other terms. For Carnap, these would be terms of science, of empirical science, typically, okay? And then we would specify semantic rules for that object language, right? Like a truth definition, as it were. And we would formulate that in a higher order meta language. And the meta language would also include an epsilon operator, would also include logical in the framework as a term, and would also have syntactic terms, because we are now doing semantics, and every semantics needs sort of syntax as a background, and so on, okay? And then the framework will be given by a class of semantically possible worlds, such that every way of assigning extensions or interpretations, if you like, to the primitive descriptive terms of the object language gets realized by some world in that class. Okay, so you run through all combinatorial possibilities of assigning, as it were, extensions, right, interpretations to the primitive descriptive terms of the object language, right? And then you define truth in a model, right, in a very much Tarskian manner, but such that the semantic rules of the framework are satisfied. And one of these semantic rules, as it were, will be given by our definitions of membership and sethood as presented in the previous part of my talk. Okay, that's the framework, roughly speaking. Okay, now what would be a scientific theory, a proper theory in the framework? Well, semantically speaking, it would be given by a proper subclass of the class of semantically possible words. Okay, so a scientific theory, right, doesn't leave everything open about what the empirical world might be like, but rather excludes way the world might be like, right? So some semantically possible worlds, right, ways the world might be that are sort of compatible with the semantic rules, they might be excluded by the theory, because the theory says, no, the actual world is not like that, because the theory is the theory of relativity theory, right? And hence the non-relativistic universe is excluded, right? And the corresponding semantically possible worlds will then be excluded from the theory. Semantically speaking, the theory corresponds to a proper subclass of the overall class of all semantically possible worlds, okay? But I'm not interested in that here. Okay, I just wanted to mention it. I'm interested in the full class of semantically possible worlds, because that is what comes with the framework. Okay. Now, you might have some worries here. Didn't Quine show that analyticity, either doesn't apply to anything, right, or is even incomprehensible, right? Is not clear enough and so on, right? Two dogmas of empiricism. That's not what I'm dealing with here. Okay, because mostly Quine was dealing with analyticity in natural language. But I'm dealing here with analyticity in a formally constructed framework, and that's different, okay? If you want to talk about it, we can talk about it later, but don't worry about it, okay? I'm not reducing analyticity to metaphysical, I'm not reducing metaphysical necessity to analyticity or so, right? So Kripke told us we shouldn't do that, and I'm not doing that. I'm not dealing with metaphysical necessity at all here, okay? So don't think I make any Kripkean mistakes here. Mistakes diagnosed by Kripke, that's not the case, okay? And then there is a philosophical debate on other notions of analyticity. Bogossian distinguishes between metaphysical and epistemic analyticity. But what happens is, my notion of analyticity is neither of that. It's semantic analyticity, a semantic concept in the same sense as Tarskian truth is semantic, okay? So don't think that's a worry there either, okay? Now, here are the semantic rules, and I don't go through them now in detail. Let me just tell you what happens, okay? So I spell out here, under which conditions a formula in the object language is true in a model M, where this model is one of the semantically possible worlds, relative to a variable assignment S. And this is just like doing semantics today or model theory today, if you like, okay? Now, the interpretation of being married and man, this is determined by the model. So different models assign different extensions to the predicate married and man, right? As we would now have it in model theory, right? Now, the interpretation of bachelor is given by specifying this semantic rule, and you can see what happens here. Basically, I write the definition of being a bachelor as being an unmarried man into my semantic rules, which will have the effect that X is a bachelor just in case X is an unmarried man. That equivalence, universally quantified, will turn out to be analytic in the framework. Okay, so these are my semantic rules. Explicit definitions will sort of be encoded in the semantic rules. Okay, for logicality, I just sort of translate the object predicate into the meta-language predicate logicality, because I think of it as a logical primitive that comes with the framework, okay? Now, the definitions of membership and sethood, these are just meta-linguistic versions of the definitions through epsilon terms that I mentioned before. So here I use my definitions 1 and 2 from before and write them into my semantic rules of my framework, as promised, okay? And which is also why these definitions will turn out then ultimately to be analytic in the framework. Okay, and the rest are just Tarskian truth clauses, okay? But of course, I have something like a meta-linguistic epsilon term that I use to interpret the object linguistic epsilon term and so on, Okay, and then I define a sentence in the object language to be analytic in the framework, just in case it holds true at every model for every variable assignment, as promised. Analyticity, semantic analyticity, is truth in every semantically possible world of the framework. Okay, and then what happens is, all logical truths are analytic, right? The definition of being a bachelor is analytic. Okay, our definition of membership is analytic. Okay, the Carnap sentence is analytic. The existence of bachelors is not analytic, so it's not that everything is analytic that is true. Of course, there are bachelors, but that's an empirical truth, right? And in fact, it's not analytic here, right? There are models in which nothing is a bachelor, okay? But now what happens with our Ramsey sentence, right? That was the thing that was interesting to us. And if you then crunch the machinery and apply the semantic rules, what you would find is, right? That's the upshot here. The Ramsey sentence, this existence claims, comes out as analytic, just in case, right, now stated in a meta language, there is an R and an S such that set F2 of R and S. Okay, and that is because analyticity is truth in every model, and truth of this Ramsey sentence in a model in a variable assignment boils down by the semantic rules to there just being an R and an S, and you can see there is no reference to the model here anymore or to the variable assignment. Okay, it's sort of absolute what you get, and this absolute statement, right? If and only if it is the case in the meta language, as it were, then the object language Ramsey sentence will be analytic, okay, in the framework. That's the outcome, okay? And why is that so? It's a consequence of our definition of analyticity, the semantic definition, the semantic rules, and the fact that the Ramsey sentence, sorry, I missed there is an RS here, okay? So this is the Ramsey sentence. The fact that the Ramsey sentence only includes logical symbols, okay? That's the only thing that you need, okay? So, for bachelor, right, this is not a logical symbol. This would be different, right? You couldn't derive that. But for the Ramsey sentence, because it only includes logical symbols, as argued before, you get that as a result. Okay. Now, there's further things that I could say here about this. They might be relevant to the Q&A. Okay. But let me just move on to my final part, and then I'm done. Okay. In 5 minutes, I'll be done. Okay. So the remaining question is, are there R and S such that set F2 are of R and S, right? Because if there are such, now expressed in our meta language, then we know the object language Ramsey sentence will analytic, and then, standard pure mathematics will be analytic as mentioned before. And now that's the final idea that I have in my talk. The fact is there something that satisfies set F2, as it were, right? Because that's a kind of a satisfiability claim, but expressed in a higher order language. And the answer is, well, no one knows conclusively, right? We cannot derive this existence claim from uncontroversial principles, let alone from logic and definitions. And that is why sort of traditional logicism, a la Frege and so on, doesn't work, I think, okay? But here's a fact. Ordinary mathematicians just presuppose, right, that there must be something, there must be an R and S that satisfies this open formula. And the reason is they presuppose very often set theory in the background. And from set theory, right, you get by, second order logic, this existence claim. So they must think, as it were, or at least presuppose, accept, as it were, that the existence claim holds here. And if you ask set theorists, right, then a long story cut short, they also believe that this is true, right? They even believe, as it were, that there are sets R and S that would do the job, right? They don't even have to be proper classes, although proper classes would be fine here for my second order purposes, right? And the reason most set theorists these days believe that there are even sets that would do the job is because most set theorists these days believe that there are strongly inaccessible cardinals, right? So really large cardinals, as it were, okay? And by the existence of large cardinals, right, you get this existence of strongly accessible cardinals, and by this you get even set theoretic second order models, okay? And from that you get the existence of an R and S, such as set F2 of R and S, okay? So now the set theorists, they can't derive that from uncontroversial principles either. But if you ask them, then they strongly believe that there are an R and an S such that set F2 R and S. Okay, so if we talk at this meta language level, and if you were to pose the question to them, is there an R and S such that set F2 R and S? Because you're the experts, right? I'm dealing with second order set theory here. They would say, yes, this is really, really likely to be true. Okay, so if you made that precise in Carnapian terms, right, this really, really likely to be true would correspond to a rational degree of belief function defined on the meta language of our framework. And we would reflect what the set theoretic community thinks by assigning a really high probability to the R sentence of, say, 0.99 or maybe even 1. Okay? From which we can conclude, although we cannot be absolutely sure that mathematics is analytically true, but we can conclude that it's very likely that mathematics is analytically true in the framework, right? Because it comes out as analytic if that Ramsey sentence is true, and it's really likely to be true. So it's very likely that pure mathematics is analytic. Okay, so here we defer to the set theorists, right? Just with respect to that higher order existence claim, not logicism as a philosophical doctrine, because they're the philosophers are the specialists, not the set theorists. Okay, and I think this also nicely reflects mathematical practice because, you know, sort of in the framework, right? If this higher order existence claim holds in the meta language, then the Ramsey sentence will be analytic in the framework, which means sort of everyone talking within the framework in the object language has to presuppose it to be true. That's exactly what everyday ordinary mathematicians do. They sort of by acceptance assign probability of 1 to it. Okay? But within the framework, that is on the level of the object language of the framework, you cannot justify that existence claim. You cannot justify it internally. And mathematicians, ordinary mathematicians, do not justify it internally. Okay, but if you look at it sort of from the meta-linguistic point of view in the framework, we're still in the framework, but on the meta level, right? We assign to it just a probability of 0.99, which means we think it's very likely to be the case that there is an R and S such that blah, blah. And this means sort of, you know, again, in that framework, that the object linguistic Ramsey sentence is analytic, spelled out now in meta-linguistic terms. Okay, that's the idea. Okay, that's it. Now, you can spell that out in fully probabilistic terms. Just if you worry there is a problem with the probability theory, it's not. If you're interested, you can ask me later. Okay. So I've argued for Carnapian Logicism. There is a logicist framework in which membership and set are defined in purely logical terms, and the axioms of second-order set theory are likely to be analytic. Okay. The essential feature of this Carnapian Logicism is not that, you know, mathematics thereby gets a more secure logical foundation. You might have hope for that, maybe, if you're Frege, right? A kind of epistemic foundationalism. But that's not the Carnapian logicism that I've presented. You don't get that. In fact, at the end, I was asking the mathematicians for advice, right? So I can't get more security for math out of my logicism, obviously. But what it shows is, right? It shows that mathematics can be rationally reconstructed as purely conceptual, as coming with a conceptual framework. And that I find interesting. And that's the logicism that I wanted to defend, okay? And all of that still stayed reasonably close to mathematical practice, I think, okay? Which overall doesn't sound like a bad package to me. Thank you.
Okay. Let's first thank the speaker for this very wonderful lectures. Okay.
Thank you. Thanks so much.
Get some claps. Yeah. Yeah, for me, this lecture is about an original, foundational, and inspiring work. Even if, anyway, I didn't follow some part of it. Okay, now I give time to I give time to Professor Macalati. Okay, please. Professor Macalati, you mute your
Oh, try again. Okay, worked that time.
Hello.
Great. Hi, nice to see you. It's a fantastic talk. You covered a lot of stuff. But what I'm left with is the basic question. Then, what is the epistemic status of, say, consistency of ZF? Is it just an article of faith? We say mathematicians presuppose it, therefore it's in the conceptual framework we'll use. There's no question about it. We just say, because I'm not convinced they do presuppose it, because they do talk about reasons for believing it in textbooks sometimes.
Okay. Excellent question, of course. So I think I would want to defend that standard mathematicians. So, you know, number theorists, okay? You know, probability theorists, okay? Algebraists. I would say it's a fair description that they presuppose sort of the truth of my Ramsey sentence, okay? As it were, the satisfiability of second order set theory, okay? but they also sort of defer to the specialists themselves. Okay. And this is what you get sort of on the object language level of my framework. On the meta level, right, where I ask the set theorists, right, there is more that we can say. And of course, set theorists, I would say, sort of people working in the foundations of math, they have, of course, their reasons to believe it to be true, right? So it's not just a willy-nilly acceptance that they could just as well have accepted something else, right? There is a nice package in this textbook that I cite here, Rubacek and Czech, okay, where they sort of sketch a little argument effectively for the existence of strongly inaccessible cardinals. Okay, and the idea that they have is, roughly speaking, right, they think we have first of our universe of, they call it first order sets, okay, but then a mathematician might come along, sort of a higher order set theorist, that closes that off, right? Packs everything together in what now becomes sort of a second order set. And then, of course, continues to, apply the usual set theoretic operations, right? Power set and union and so on, and builds another universe on top of it, right? And thereby gets new ordinals. And then the first second order ordinal that wasn't already there, that's the strongly inaccessible cardinal, right? And therefore, by that package, since we thought sort of, now we can, in a sense, reflect back the ordinals that we wanted to have were all the ordinals, as it were, right? So the second order ordinals, we can think were already there amongst the first order ordinals, right? So we already should have had the strongly accessible cardinal already in our first order universe. So hence there are sort of strongly accessible cardinals, right? This is roughly an argument there. Of course, it can't be really carried out in ZFC, first order ZFC, and right? Of course, they say so, but it's at least a kind of, as it were, intuitive argument that gives some kind of credibility, right? Because it still uses sort of the underlying spirit of how we build the cumulative hierarchy. And I can use sort of the same kind of argument here. I can't use it on the object level, but I can use it in the meta level. So that's at least something that I can put forward. It's just that this is not original to my logicism. But here, I just defer to what the set theorists have as reasons that they put forward anyway. Does that help, Colin?
Well, yeah, it's an interesting position to take and to pursue. I like this framework a lot, but then it leads me to another question about the continuum hypothesis.
Yes.
Is that also something we'll just wait for people to form a consensus on, or are there reasons?
No, that's an excellent question. So, there could be a reason to think that what I just said would also apply to the continuum hypothesis in much the same way, because I'm doing everything in terms of the second order level, right? And then the axioms that we have pin down the structure, as it were, right, up to the height, right? But the continuum hypothesis lives sort of really low down in that structure, right? So you might think, actually, for very similar reasons, it has, in a sense, a determined truth value, right? Of course, we can't derive it, right, in second order, the deductive system that I've just described in the axiomatic system, right? But, if it holds, right, then actually the corresponding object linguistic statement will be analytic in the framework, right? And, we might wait for the set theorist actually to find out about that. Okay. Mm-hmm. So, and funnily, and that's interesting, right? There is a passage where Carnap says exactly that about the continuum hypothesis. Mm. And it's in a really late interview of Borchardt. It's the person that I mentioned before, who wrote this paper on Carnap's logicism. And he was a friend of Carnap's, and he interviewed Carnap sort of on these foundational questions. And that's where Carnap says pretty much something like that, not using the machinery that I'm using, but coming to something like that effect. Okay, so I think I would go there. Yes.
Oh, okay, great. Just a tiny question: how would you relate this to Takeuchi's exposition of type theories? Your second order, is that like Takeuchi's second order, or just a bibliographic question? Really, I happen to know Takeuchi's book.
Yeah. I wish I could answer that competently, but I can't, Colin. I don't know. I would guess if you say you don't like, the precise way I've written up, sort of,
No. I'm just
feel-
asking. I'm asking for more help so I can understand the precise way.
Excellent. I promise to check it out, and when I write the paper, which I'm currently doing, I'll have something to say about it. But I don't really know. I don't know.
Great. Yeah. Are there questions from the audience?